All right, on to part two of today's lecture. We're going to cover interactions. And interactions are a really flexible tool that we're going to see often in regression. And effectively, what we're doing in an interaction is allowing the relationship between some predictor y and some outcome x to be conditional on a second predictor z. So we're saying that the relationship between x and y now systematically varies as a function of some other variable. Now, as we kind of go through interactions, you are going to hear me talk in language that is commonly associated with multi-level modeling, where we're going to say it has a variable slope or a variable intercept. And I just want us to start thinking generally in those terms, right? We're going to allow, in the context of interactions, we're going to allow models to have slopes that vary as a function of some other variable. And this is going to be a really flexible and powerful approach. Okay, so the motivation is that a linear model assumes that predictors are independent and assumes that the relationship between some variable x and y can be estimated in a way that doesn't depend on any other variables. It tells us about the expected relationship between x and y once we know z, right? So what if we think that the relationship between x and y varies based on z? So in a typical regression, we might have our outcome x be a function of our linear function be alpha equals beta beta 1x times beta 2z. But what if we think that the slope, the relationship between x and y, is different at different parts of the model? At some points, the slope might be 2. At other points, the slope might be -1, right? And an interaction is going to allow us to specify these kinds of variable relationships. So to start, we're going to work through an example of the relationship between terrain ruggedness and per capita GDP, right? We're just following the example from the book here, if you'd like to read along there. But the basic insight here is that countries with smoother terrain, less rugged terrain, tend to have stronger economies. However, countries in Africa see a reversal of this, where countries with more rugged terrain tend to have higher economic performance today than in the past. And this is likely a function of the protections that rugged terrain offered against the slave trade and against raids by slavers who preferred to make raids and capture people for the transatlantic slave trade in places with easy access to the coast, right? And so rugged terrain might have protected African nations from exposure to the slave trade in ways that could still have virtuous consequences for their economies today. So here, what we're suggesting is that terrain ruggedness has one relationship, one effect outside of Africa and a different effect inside of Africa. So let's explore the data. So we have three measures here that are going to be of interest. We have two predictors: terrain ruggedness, which is effectively just a measure of how much variance there is in the topography of a country, how many hills and valleys there are. And our second predictor is going to be continent, right? So what continent is it on? Is the country on? And here we're just going to use a binary indicator for whether the country is in Africa. Our outcome is a country's gross domestic product per capita, and that's just the ratio of total economic productivity in a country divided by population. And we're going to transform that to the log scale, because we might be interested in kind of the degree of variation across countries rather than the absolute difference across countries, rather on the order of magnitude scale. So when we estimate separate regressions, so let's say we kind of estimate one regression for countries inside of Africa and one regression for countries outside of Africa. So we split the data into two data sets, and then we run separate models on them. We get this relationship. So the red is non-African nations, where we see terrain ruggedness being associated with declining economic performance. So countries with more rugged terrain outside of Africa tend to have lower economic performance. But inside of Africa, countries with more rugged terrain tend to have stronger economic performance, right? So here within Africa, we see these kind of low ruggedness countries all the way up to these high ruggedness countries. And these high ruggedness countries tend to perform better inside of Africa. So we have a negative slope outside of Africa, a positive slope inside Africa when we estimate separate models. So how could we do that if we kept the data together and didn't separately estimate the regressions? And typically we don't want to partition our data in this way because we actually gain information across cases when we hold it all together. And this will become especially true when we start to get to multi-level models. So let's set up the data for analysis. The data is rugged. This is available in the Rethinking package, so you can load it with data rugged. I'm going to go ahead and set up my log GDP. And as per usual, I'm going to scale. So first I'm going to create log GDP as a logarithm of this RGDPPC. That's real gross domestic product per capita in the year 2000. And then I'm going to scale the logarithm, right? So first we're going to log transform it, then we're going to scale it onto that mean centered standard deviation scale. And then we're going to scale our terrain ruggedness variable. And we have some missing data here, so we're going to filter out those cases that are missing data on the log GDP variable. Our first regression model is a single predictor where we're going to have an intercept with a prior normal 0, 0.1, right? So that's a pretty narrow prior centered on 0, centered on the mean, and beta prior 0, 0.3. Again, pretty narrow. Feel free to, if you want to see some motivation for these priors in the prior predictive simulation, those are described in the book. But here we notice that we see a very near 0 slope on terrain ruggedness when we don't condition on continent, right? So let's take a look when we add an intercept for Africa. Here we're going to add, we're going to take the cont Africa, which is currently 0, 1. We're just going to move it up to 1, 2 to allow us to estimate the intercept in this way. We're going to now allow varying intercepts. So we're going to have one intercept for countries inside of Africa and one intercept for countries outside of Africa. We're going to use that same 0, 0.1 prior, right? So effectively, we're going to say that, countries outside of Africa could be in one place, countries inside of Africa could be another. And we do see that we've got a clear difference in intercept here. Those countries outside of Africa have a positive intercept, and those countries inside Africa have a negative intercept. And we see now the slope is slightly higher and negative, which is what we see when we include, when we subset the data to outside of Africa. So let's see what these model expectations look like. So here we're going to, as we have before, we're going to scale. We're going to run ruggedness from the observed minimum to the observed maximum. In this case, it runs from -1 to 4, right? And we're going to create 100 scenarios. But what we're going to do is we're going to repeat that twice. And that's because we have this categorical variable cont Africa in here. So this code's a little funny. Unlike just a typical sequence here, we're going to create the sequence -1 to 4, 100 long, and then we're going to repeat that sequence twice. And the reason we're going to do that is because we want to have the entire range of terrain ruggedness, -1 to 4, available for simulation for those countries inside and outside of Africa. We're going to indicate that with the cont Africa variable. And to set this up for simulation, we're going to take the values 1 and 2 and then repeat each of them 100 times. I just want to show you what this looks like in R so you can get a sense for how we're setting up the data. So here is where we're setting up the counterfactual, okay? So let's take a look at what this looks like. Now, when we take a look at the full data frame that we've just created, we're going to have 100 values that range from -1 here up to 4 here. And you'll notice that the first 100 of them are all assigned to cont Africa 1. So that's going to be our scenarios for outside of Africa. And then we're going to start over -1 all the way to 4 with the next 100 values. And those are all going to be inside of Africa, where cont Africa equals 2. So what we get is we get this 100 length sequence, right? But we're going to repeat that twice because we want it inside and outside of Africa. And then we're going to repeat the sequence 1 and 2, but we're going to repeat each value 100 times, right? And so when we stick those together, we get a data frame that has all the values we need to run the link function to draw posterior samples of mu, right? And as we've done before, I want the maximum a posteriori estimate, the mean of the posterior, and I also want the 89% percentile interval. And then I'm going to set that up for plotting, right? As we've done before. And just so you can see what this data frame looks like. There we go, right? We have the terrain ruggedness measure. We have the Africa continent measure. And we have log GDP at the mean, lower, and upper. And that's all we need to run everything through ggplot. And here's what that model looks like. To just briefly walk you through the ggplot code, right? Of course, our data is plot dat. Our aesthetics are, as we've done before, on X is our focal predictor. On Y is our outcome, log GDP, which I've set to be just the mu mean right now. And I'm going to use this group aesthetic argument to make sure that R knows that the lines should be drawn by group according to Cont Africa. We're going to give the lines a color for Cont Africa. And we want to make sure to specify factor so it doesn't put these on a continuous gradient. If we don't, it thinks that 1, 2 is just a continuous measure. So it'll give us shades rather than distinct colors, which is what we want here. The ribbon we're drawing as per usual. And then I'm going to add the geom points on just so we can see the distribution of those points. Now, what's important to note about this model is that we do see those different intercepts, right? Where the green blue line indicates the estimated relationship for African nations. The red line indicates the estimated relationship for non-African nations. But unlike the initial model where we saw varying slopes and varying intercepts, here we only see varying intercepts, right? The slopes of the line are identical. And that's because we specified the model as such, right? The model still has one beta parameter. So there's no way that the slope for the African nations can be different than the slope for the non-African nations according to that model. So how do we get there? The linear component of our Africa, not Africa intercept model is alpha Africa sub I, right? Where we allow each nation to have an intercept determined by whether it is in Africa or not, and then a beta for ruggedness, but that doesn't vary across countries at all. So we get one intercept for the African countries, one for non-African countries, and the slopes are identical. So how do we add that interaction? We can proceed similarly to as we did before. We can allow nations in Africa to have one slope and nations outside of Africa to have another slope. And effectively what we're doing here is we're interacting the variable Africa with the variable ruggedness. We're saying multiply Africa by ruggedness, get one slope for Africa, one slope for ruggedness. So here we have a variable intercept for the African nations and non-African nations, and a variable slope for the African nations and non-African nations. Now the effect of terrain ruggedness is conditional on whether or not the country is in Africa, right? So we've built an additional conditional relationship here. And that beta Africa, allowing there to be two slopes for the ruggedness variable, is the interaction, right? The slope of ruggedness depends on continent. So let's take a look at this. That's our model, right? We're going to estimate it in a pretty straightforward way, where we're going to use bracket indexing to allow there to be two alphas and bracket indexing to allow there to be two betas. We're going to use identical priors for both, right? Where we're specifying the priors for both alpha continent Africa equals 1 and alpha continent Africa equals 2 as normal 0, 0.1. And the beta for continent Africa equals 1 and continent Africa equals 2 to be normal 0, 0.3. Now, we're going to use this compare function just to get our heads around kind of what these models are telling us, right? So M8.1 is the no Africa intercept model. M8.2 has the Africa non-Africa intercept. And M8.3 includes variable slopes. So we have both here variable intercepts and variable slopes. And we can see that WAIC prefers the intercept model, right? Prefers the model in which we have both variable intercepts and slopes. We can see that the difference in WAIC compared to the variable intercept model is about 9 lower. It's a huge improvement over the model with no variation, without any measure of continent. The standard error is not a tremendous improvement, right? So we see here a difference of 9 with a standard error of 7. So we're not the WAIC is not cleanly indicating that 8.3 is a better predictive fit than 8.2, but it is an improvement, right? So let's proceed, right? This is kind of one way we can think about model comparison is here we have better fit the data in a way that the WAIC score, so despite the penalty, it appears to indicate that we're going to get a better predictive performance out of a model like this, despite the added complexity. Okay. So let's visualize this interaction, right? We're going to do it similarly to what we just did. Where we're going to use the link function to draw posterior samples of mu that average over uncertainty in both of our alphas and both of our betas. We're going to do apply to get our mean and our PI, and then we're going to set up the plot dat just as we've done before, right? And here's the ggplot code, very similar to what we just did. And here what we can see is that not only do we have one slope for the non-African nations, or one intercept for the non-African nations and African nations, we have a different slope. And again, as we saw at the beginning, right, we have this negative slope for countries outside of Africa and a positive slope for countries inside of Africa. Except instead of splitting the data in two and estimating separate models, now we've estimated it within a single model by specifying that interaction term. So let's just go back real quick and take a look at that first model. Here it was there, right? And this is what we've ended up with in our interaction-based approach, right? So we've recovered that two-slope structure with the interaction model. Now, when we do this categorical by continuous interaction, we can specify it exactly like this, right? Where we can just estimate a single slope for each value of the categorical variable that we wish to interact that continuous measure with, right? So if we think here, maybe we wanted to estimate, maybe we didn't think it was only Africa that might have seen this variable terrain ruggedness effect. Maybe we thought other nations might have seen it as well. Then we could estimate potentially a slope and intercept for each continent, right? We could extend this as far as we like. But the approach is really flexible and really general. We could, in theory, estimate one intercept for each continent and one slope for each continent. But what if we want to fit a model where we interact? So this again was a categorical variable interacting with a continuous variable, where we allowed the relationship between the continuous variable and the outcome to be conditional on a categorical variable. But what if we wanted to condition a continuous measure's relationship to an outcome on a second continuous measure? Now, in the categorical by continuous example, we're going to get k slopes, right? Where k is the number of categories in the categorical variable. But if we interact two continuous variables, we estimate an infinite number of slopes, right? We don't have the clean kind of, well, there's Africa and non-Africa. What if we're interacting two continuous variables? They can take on as we can subdivide steps along a continuous variable an infinitesimal number of ways, so we end up with a potentially infinite number of slopes. And directly interpreting posterior parameter estimates in this context gets really difficult. You notice even in the example of the categorical by continuous interaction, I wasn't actually looking at the table of parameter estimates. I instead turned directly to visualization, and that's going to be my general recommendation when we're dealing with interactions. You shouldn't be examining coefficients in this context. You should be going directly to data visuals. They will really clarify what's going on here. So let's think about this continuous by continuous interaction. We know that plant growth depends on light and water, right? If we've got light and no water, there's no growth. And if we've got water and no light, there's no growth. So here we're going to look at how the number of blooms on a tulip vary as a function of light exposure and water exposure, right? So we know here that one variable can't work without the other. So both have to be at a high level for there to be growth. If either of them is at a low level, there's going to be no growth, right? So we have an interesting kind of modeling problem here. And this is one where we need to interact the water variable with the shade variable to understand what's going on in blooms. So let's take a look. First, we're going to fit a model with no interactions, right? And that's just going to take on the typical format we've seen before, alpha plus beta W water plus beta shade, right? We're going to transform the variables following the example in the book, where we're going to constrain blooms to take on values between 0 and 1, right? So by dividing it by its maximum, we make 1 equal to the maximum value. So effectively, it's how much smaller, how many fewer blooms did this plant have relative to the largest number of bloom plant. And we're gonna water currently takes on values between 1, 2, and 3. We're gonna pull that off and make it range between -1 and 1, and the same with shade. We're gonna make it range between -1 and 1. This is our initial model. These priors, because of the way we've scaled it, are pretty sensible, but feel free to go conduct some prior predictive simulation if you'd like to explore in more detail what appropriate priors for this case might be. Now, how would we add the interaction here? What we're going to do is we're going to add one extra term to the model. It's going to be called beta SW, and beta SW is going to be multiplied by WI times SI, right? So the product of water and shade now has its own term in the model, and that's going the shift in the slope now will be beta SW. So the way we can interpret this is that mu is now a function of water, shade, and the product of water and shade. And the way we estimate this model is pretty straightforward, right? We just add, in the last case, right, we had the alpha plus beta W plus water S plus, and that's just the scaled, plus beta shade times shade. Now we're going to add this term, this beta WS times water S times shade S, right? Priors are going to be identical for all of them. Okay, now this is what we're effectively saying is that the slope of the line depends on the value of water and the value of shade and the interaction of water and shade simultaneously. So what in effect this is going to do is it's going to pull the line around based on the joint value of water and shade. So now the slope of the line for water, right, is only exactly equal to beta W when shade is equal to 0, because that'll zero out this other term. And it's only equal for shade to beta S when water is equal to 0. Otherwise, these slopes are modified by this extra term. And this gets really difficult to interpret really quickly, as you'll see. Right here, we're going to compare the models again just to see if we've improved fit by adding the interaction. And here you can see WAIC for tulip 1 is much lower than WAIC here. Again, the standard error difference is not is about as large as the difference. So the WAIC measure is not completely certain that this is an improvement in fit, but it is a stronger fit for the model. And the weight parameter is giving a lot to tulip 1. So we've better fit the data. Here is the table of posterior parameter estimates. Okay, so alpha, we understand what alpha is, right? It's the intercept, same as it's always been. Now beta W is the slope for water when shade is 0, right? Beta S is the slope for shade when water is 0. And beta WS moves the slope by W times S when neither of them is 0. right? And this is incredibly difficult to interpret. I've said that a bunch of times already. I hope you internalize it. Don't pay too much attention to parameter tables when we have interactions. They become incredibly difficult to interpret. Visualization is where you should turn immediately to try and understand interactions like this. So let's do that. It's going to be a little tricky to set up though. So the plan is to visualize the counterfactual relationship between water and blooms for a range of values of shade. And this is going to mean multiple plots, right? So because we have, water and shade in theory could take on infinite numbers of values between -1 and 1. So what we need to do is we need to split that up into a discrete number of categories for one of the variables. Because we're focused on water here, what we're going to do is we're going to break shade into a fixed number of ordered categories, right? So we're going to say, okay, it ranges from -1 to 1. Let's explore that at 3 points. Let's explore it at -1, at 0, and at 1. We're going to get a full range of water along those 3 values of shade. So if we want to see k values of water and j values of shade, we're going to end up with k times j scenarios in the counterfactual data. And this is going to look a little funny as well, and I'll work through it with you real quick. So let's take a look. Okay, here is our code for plotting. Okay, now this is what we're ultimately going to end up with. As we did before, we take a sequence from -1 to 1 with length out of 10, and that shouldn't look too surprising to us at this point. But we know we're going to take 3 scenarios for shade. We're going to take -1, 0, and 1. So what we want to do is we want to repeat this 3 times so that for each value of shade, we get the full range of water scenarios, right? So here are those first 10. Here are the second 10. And here's the third 10. And onto this, we need to pair the range of shade that's appropriate. So here we know we want to go -1, 0, 1. But we have 10 water scenarios, right? So we want to repeat each one of these values 10 times so that those first 10 water values get paired with the -1 shade value. The second 10 get paired with the 0 shade value, and the third 10 get paired with the third shade value. And again, once we stick it all together, we end up with a 30 k by j number of rows, right? So where we have the water sequence repeat 3 times. And then, so that's for the first shade scenario, the second shade scenario, and the third shade scenario. And now let's plot it. Okay, we're going to do link and then our 2 apply functions as per usual, right? We're going to stick those on with a mutate onto plot.dat. And we're going to ggplot everything. Again, our aesthetics are going to include water on the x-axis. Y is mu, because we named that as our mean. And then we're going to define the ribbon with the minimum and maximum, right? Going to add line and ribbon to it as usual. But now because we have these 3 scenarios, I want to use a facet to basically pull those apart so we can see them in sequence. So I'm going to facet wrap by shade, right? So I'm going to get 1 plot for each value of shade that exists in the data. And here is where we can really see what the interaction is doing. We can see that when shade is -1, right, the expected value of growth, that means, so there's basically no shade, full sunlight, right? The expected relationship between water and plant blooms is quite strong, right? So under full sunlight, as we increase water, we get a very steep increase in the number of blooms. Now 0 is partial shade, right? And there, as we increase water, we see slightly less plant growth, right? So here we don't get quite as much bang for our buck for water as we do in full sunlight. And here in full shade, we see very little additional benefit of water. Our change in expected blooms is very small going from no water to full water in the context of full shade, right? But note for each scenario, right? If we've got no water in the full sun, we don't get much growth. No water, no growth. No water, no growth. What differs is the amount of growth we get from adding water based on how much light there is, right? So this is, once we visualize it, this kind of changing slope relationship becomes pretty easy to see. But if we're just looking at this table of parameter estimates, it becomes really difficult to imagine what's going on here. So let's push this a little further and break this out to 9 scenarios, right? So here was 3. If we really want to see exactly how this variable slope works, right? So here we're going from -1, minus 0.75, minus 0.5, and we can see this gradual decline in the magnitude of the slope as shade increases, right? As we go across the facets, we can see how the slope becomes more and more shallow as we decrease light, right? The expected growth of a plant for increases in water goes down as light goes down, right? And this is the nature of these continuous interactions, is they allow the relationship between one variable to systematically differ as a function of another, right? So now the expected change in blooms for different levels of exposure to water is conditional on how much light the plant is getting. And this makes perfect sense for this kind of relationship, and it makes perfect sense for a lot of other kinds of relationships. This is a really powerful and flexible tool that we can use in regression. So that's it for today. The homework is going to be problem hard number 4 from chapter 8 of the book. And this will ask you to use the tools that we've kind of been exposed to briefly here today from chapter 7 in terms of model comparison, especially using WAIC. But it'll also allow you to practice using your intuition to think about interactions. And this will be a challenging homework. I need you to, spend some time on it, and we'll certainly make time in lab to discuss the material from today and also initial questions that may come up about the homework. Thank you again for your flexibility in moving this online today, and I will see you next week.